Alright, this is part 2 of chapter 11, where we left off on this figure in part 1. And just to finish up, what you see down here in the blue lines, both CD4 positive here, CD8 down here, the blue bars here represent individuals who were only immunized once, whereas the salmon or magenta or pink bars here represent those who were vaccinated twice against vaccinia, specific antigens, the virus. And what you can see is that in all reality, one vaccine, one exposure is actually fairly good at maintaining high levels of T cells. And it's not until nearly 5 to 7 decades after that exposure that those individuals who had 2 vaccines, 2 exposures, actually had more cells. So it's good to know that our immune system can actually do a very good job even with just one exposure. Alright, then with looking at why the immune system is so much better during that secondary response. Looking at the source of B cells, alright, with the secondary immune response, you need less pathogen to actually induce the secondary immune response, and that is a faster response, alright. The reason is that here with the unimmunized donor, the antigen-specific B cell hasn't been identified, it hasn't been activated in any way. So you're looking for a B cell in a population of 1 in 10,000 to 1 in 100,000 for that one B cell to be circulating through the blood, to be moving through the lymphatic system to find that antigen. However, if that person has been immunized, then their system has already gone through that phase of that primary immune response. And so they have, during that primary immune response, one of these B cells in this high number found the antigen and were able to go through differentiation and clonal expansion. And so now actually the frequency of that antigen-specific B cell is actually quite high, 1 in 100 to 1 in 1,000. And so in that case, it doesn't take nearly as long to find that specific interaction and to induce the response. In the primary immune response, isotype of antibody produced are IgM, G, A, and E. IgM is the first antibody to be made, but following that second response, the B cell, the memory B cell, has already gone through that initial stage of isoclass switching, isotype class switching. And so now there isn't any IgM that's going to be made. Alright, it's all IgG. Alright, the affinity and somatic hypermutation level is low in this primary response, but high in the immunized donor during that secondary response. Alright, so what's the difference between first and secondary response? Alright, here in the primary immune response, it's the naive B cell that looks for the pathogen. And then you just go through the same process that we've talked about all semester long, of that naive B cell being activated, becomes the antibody-producing plasma cell, and you have low-affinity IgM antibodies being produced. Those can be effective, but not quite as high. And with the secondary immune response, you already have antibodies in the system that can then go to find that antigen and neutralize it. Alright, and then in some cases, if this antigen is coated with antibody and it gets close to a naive B cell, what's going to happen is interaction between the Fc gamma, so that would be the Fc receptor here, right, interacts with, or the antibody interacts with the Fc receptor here, gives this cell a negative signal and causes the IgM cell to be downregulated. All right, so there's actually no production of low affinity IgM antibodies. But rather, over here, the direct interaction between the pathogen and the memory B cell causes this cell to receive a positive signal, immediately drives that cell to become now an antibody-producing plasma cell, and the cell produces high affinity IgG. And so that's good. In this scenario, though, right, when you have a secondary immune response, you will actually see some IgM being produced. It's low levels, but the reason for that, because if you see here, you might say, well, since this cell is expressing IgM and it gets that negative signal, then it's not going to do anything. Well, if the naive B cell first interacts with this pathogen, and this pathogen does not have any antibody bound to it, then the antibody can't bind to the Fc receptor to give that negative response. So if you take this part out, then you still have the antigen binding to the B cell receptor, activates that naive cell to start this process over. All right, so both of these, or actually all three of them, can occur at the same time during that secondary immune response. All right, this can occur, and so you have a lot of the secondary response going on, but you could also have a little bit of the primary response going on because B cells are always being regenerated, and so you always have potential new naive B cells to help fulfill any delinquencies, any holes in the immune response there. All right, then if we focus on the antibody production over here, all right, the concentration of the antibody, similar to what I was talking about before, where you have the first exposure, and this is specifically looking at immunization. All right, the first exposure at time 0, with the antibody present, you do have more IgM being produced than IgG. It starts faster, it goes higher, but it also drops off quicker, the IgM levels, than the IgG. All right, then you have the secondary response, or secondary exposure, to give that secondary response. And now you still have a little bit of IgM being produced. All right, so that's similar back here, except some of those naive B cells are being downregulated, so they're not going to do anything. But you have a few naive B cells who run into that pathogen and go through some amount of differentiation and expansion. All right, but this is the important one here, where IgG, huge increase. All right, much greater than before. Much higher difference between IgG versus IgM. Third exposure, even higher IgM levels, and very little of IgM. All right, then antibody affinity, how strong is the antibody? All right, IgM, while it's good, all right, it's relatively constant in the affinity of the antibody produced, whereas IgG, much better because it always increases. All right, then in viral infections, you actually don't have many T helper cells, effector T helper, CD8 positive T cells, giving rise to memory T cells. A lot of those cells will die off. And if you read the textbook, you'll see that it's about a 95 to 5%, where 95% of effector CD8 positive T cells will die, and only leave about 5% of those cells to be memory T cells to be able to hang out and be ready for the next onslaught. What this figure is supposed to represent is someone who has, who is positive for CMV, human herpes virus, and this patient has a transplant, and so is on immunosuppressive drugs, and right away that CMV is able to pop out because of that stress, increase high numbers, and then it takes a while for the T cells, specific T cells, to increase, All right, but during this time right here where you have a huge increase in the number of T cells, that is direct correlation with the sudden drop-off of the viral load. Once those CMV-specific T cells are produced, they're able to become activated and kill off the virus level, and then they will maintain some levels here and have the ability to keep the virus at bay there. Alright, then this is a pretty cool figure here where it shows what is called the original antigenic sin. Alright, so what you have here is a first infection with this virus. Let's say it is influenza. You get infected or vaccinated against, well, we'll go with infected here. Alright, your body hasn't seen it, and you get pretty sick. You are in bed for 14 days, and this is the primary response. And in that primary response, your body makes antibodies to all of the different epitopes here, and you've got high amounts. And so then the virus goes away, and you get healthy. All right, the second infection, now after some time, all right, you have, or this virus mutates, and so now it's lost one of the original antigen epitopes. It's gained a different one, but in this response, you don't get antibodies made to antigen E, all right, because of this reason. This is a new virus that goes through this process, but this virus is going to get bound by these three antibodies, and then the antibodies bound to this virus are going to inactivate naive B cells, and so there's no way that the cells can make an antibody to E. Alright, same thing here. As you increase in time, you have less of an ability to make a response against this, even though it's a new virus, newer virus, different virus, and so it actually still makes you sick. Alright, here you don't feel too cruddy, alright, but as your immune system wanes because it can't fight this newer virus, you get more sick. Until this fifth infection now, this is a brand new virus that your system could have potentially made antibody against, but it couldn't because it always had that original epitope still present, which has kept the immune system from making any response. And so now with this fifth infection, brand new virus, officially your body hasn't seen it before, according to the immune system, and you're back here at being in bed for 2 days. All right, this process is actually, it could take several years, and it probably does. Several years for this virus to mutate like this and actually be completely different than what it was over here. So then when imprint, all right, so this is referred to as imprinting, when imprint is finally broken at this point, all right, and it said maybe your immune system repents or something, then now your body can go through the process of responding and now even start this process all over. All right, but the idea of original antigenic sin, kind of hard for me to connect with, understand, correlate that with Adam and Eve, but it's a real thing. It's a real idea. And I looked for several reviews over this, and there's actually quite a few of them. I couldn't actually get full access to them. All right, but this concept of original antigenic sin was first proposed by Thomas Francis Jr. in 1960. All right, there's a lot of debate that goes into this, right? If it really is true, if it's not, is there contradictory data to this? But original antigenic sin implies that when the epitope varies slightly, then the immune system relies on memory of the earlier infection rather than mount another primary or secondary response to the new epitopes. All right, this would be faster and stronger, but you just don't have it occur. So, just kind of interesting, and that concludes part 2 of chapter 11.